and I multiplied that by 100. But maybe it was, because what I typed in initially was parentheses 1.403 minus 1.38.
Close parentheses.
Yeah.
Divided by
0.5, then another parentheses, and added that straight across.
Ah.
Because the second time I got one.
So you had this, you did 1.403 minus 1.380
Yeah.
divided by 0.5,
Yeah.
Yeah,
parenthesis,
That's where it's
1.403 plus 1.38, like that?
Yeah. Did it? Yeah, that's what I was gonna ask.
that's where I messed up.
If you don't have those extra parentheses there, then what it's gonna do is, it's gonna divide by 0.5 and then multiply it by that number right there.
Yeah.
Okay. All right,
Order.
it's still 1.65% off. That's looking pretty good. Not as good as the, the setup numbers that we had before. Let's take a look at the torques. I think in the lab, it mostly prescribes where to pick it. I can't quite remember, or did you, Chase, you just looked at it. Do I tell you where to pick the axis of rotation, or?
Yeah, you give us 6 or 7 options, and we pick from those 7 options.
Okay. So let's pick some point, and it doesn't matter where I pick it. We have a force that's acting down, that's the weight of the meter stick, which we have right there. Let's pick that point right there as our axis of rotation, because again, I can pick it anywhere. I don't expect the sum of the torques to be 0 because these are from a physics lab. The total torque is the sum of the 3 torques.
Yes, thank you.
What is the torque? If given that blue dot over there is my axis, the left scale gives us how much torque?
Wait, are you talking about where the dot is?
Yes.
There's still a dot?
Yes.
0?
Yeah. It's like, again, pushing on the hinge. So I have 0 times 0.685. No, not 685. What do we?
Here,
Oh, it is 0.685.
is it the
Newtons. 0 meters. Plus, now we go to the weight. So that distance is, well, the difference between 49.9 centimeters and 10 centimeters. 39.9. Or to put it in terms of meters, 0.399 meters times that force, negative 1.4030736. Plus the last one. The last one is trying to rotate it about that point there, trying to rotate it. See, that's the point. Yeah, counterclockwise, thumb points out, I should get a positive torque, which I would if I, that's 0.800 times 0.695 meters.
Why 0.8?
Because this is 10 centimeters from the left side, that's 90 centimeters from the left side, so the difference between them.
Gotcha.
And so the grand total is, should be something close to 0.
.004090664.
Units? What is this, what are the individual amounts? I know I should have asked for it first, but.
Negative 0.5598,264 plus 0.556.
This is
556. Yep.
0.556?
Point, yeah.
All right, now they should add up to zero. They're adding up to something close to zero, not quite zero. So if I need to do a comparison about how far off I am, I'm gonna do the same thing I did over there. I'm gonna compare these two numbers here, or the absolute values at least. So I'm gonna find the difference between the absolute values, 0.5598,264 minus 0.556, and then I divide by the average of the two. So, 0.5598,264 plus 0.556 divided by 2. And we'll end up with some small percentage. Times 100%. So in the lab, I ask for the percent difference between the absolute values. This is what I'm talking about at this point. It's the difference divided by the average. All right. We'll assume that you can do that. If I pick a different axis of rotation, I'm going to get a different torque. Because that's just the way it works. So there's going to be the last question of the analysis, which is optional. And that is, given the actual real data that you have, where would you put the axis of rotation in order to get the absolute smallest total percent differences? Because you have 7 different setups, or 6, however many, 6 or 7 different setups. You'll have a percent difference for all of them. If you add them up, what axis of rotation will give us the smallest sum there? That is a bonus lab. If you do it, you can leave it blank, skip over that, or you can do it for the extra lab period. All right, any questions before we get to Chase's first question of the projectile motion?
I got a different answer than the negative.
Oh, then.
So did I.
Yeah,
got-
what I was gonna say is, when I got the the negative .004, I got a different number for the combination of the two right in front of your face. The
Actually,
0.55 was different for me.
just looking at those two.
Yeah. The
that
one on
gives
your,
us-
the middle one, I
Uh-huh.
got was negative .560090664.
Does that match what you were getting? You guys anything completely different?
Yeah, for this point, negative point, I got 0.0038263664.
That's what I wrote too.
It should be negative given those.
So yeah, I said negative.
All right. So I think the lesson here is, well, you shouldn't be assuming your lab partner knows what he or she is doing. So always double check. I don't know why there was a difference, but it could easily be 2 letters or 2 numbers that got flipped. All right. I have 2 masses here. If I trust the manufacturer, or if the manufacturer is to be trusted, this is 100 grams, this is 200 grams. If I fling them off the table at different speeds, which will hit the ground first? The 200, the 100, need a tie. So there's a vote for the 200. Are you gonna, it sounded like you were about to say something.
I'm sorry, I missed the question.
All right, if I fling these off a table at different speeds,
At different speeds.
which will hit the ground first?
When you say fling, are you throwing them?
I'm gonna flick them off the table so that they actually go off the table at the same time.
But what's the differences in the speed? Sorry.
How much of a difference do you need?
I don't know.
So, I hope not. No, I wanna go off the table at the same time. Who do you want me to hit?
Nobody.
Basically, I'm gonna be flicking it off like that. Because this one's farther from the axis, it's got a greater speed, so that's gonna get slung at a greater speed than this one will, which should basically just be pushed off a little bit. All right, so the 200 I'll flick off faster than the 100, if that makes a difference to anyone. So far we have one vote for the 200 gram.
I'll say 200 too.
All right, 2 votes.
Which one will hit the ground first?
Yes,
I think it'll be like at the same time.
okay, and 1 vote for tie.
The little one.
Which one?
The little one.
The little one, all right, so we got a vote for 100. Anyone else with an opinion?
We're saying which one hits the ground first?
Yeah.
I don't know.
Just do it.
I feel like I need to know the speed.
Yeah, I don't think it's gonna hit you, but,
Can you swing it the other way?
well, I wanted to do it where people can see it.
Oh.
Oh, you know what makes sense is to move the table. There we go.
Oh,
I couldn't even tell.
200 it looks
It
like.
was the little one.
I don't
I thought
know.
it was the same.
I heard it.
What's that?
I thought it was the same.
It was about the same.
Okay.
The fact that it was going faster, had more mass, we could switch them and it should come out pretty darn close. So now the 100 is gonna be going faster. That obviously not what I was wanting. So it was about the same for that one also. All right, so the lesson here is that if they're both coming off horizontally, they should hit the ground at the same time. Which means that if I dropped one at the same time the other one gets launched, they should still hit the ground at the same time. So if I fling something off the edge here, and I know how far out it goes, let's just say it goes out 1.2 meters, from a height of 0.7 meters, I can figure out how fast it had to have been launched in order to do this. Well, if I know that the time it takes for one just dropped to, the time it takes for something just to drop straight down and one to be flung horizontally to hit the ground is the same, first thing I need to do is figure out how much time does it take for something just to fall 0.7 meters from rest. I'll go back to some chapter 3 equations. If the initial speed is 0, so if I take an object, just drop it, there's the formula. It's going to go 0.7 meters is equal to 1/2 times, which is 9.8 is good enough for right now, t squared. So what I'm doing is figuring out how much time does it take to fall. Now, if we have incredibly good reflexes, we probably could use a stopwatch, but based on past experiences with people, anything under a half second is reflexes become have a very major impact, so we're gonna use the math for it. So that's 0.7 is equal to 4.9 t squared. I'm trying to find t, but first thing I need to do is get rid of the other stuff, so I have to get rid of that 4.9 first. So I'll divide by 4.9. I end up with 0.14287. Pardon?
After the 7, 1, 4.
It repeats.
Oh.
And then take the square root to get rid of the square, and you end up with something. So 0.3 something.
3.377964
Units?
seconds.
Yep. All right, so it takes about 0.38 seconds for it to fall. Now we have to figure out how fast it's going when it gets launched. Well, once it is launched, so let's say when the object's here, what are all the forces acting on it?
Wait.
Anything else?
No,
What's it touching?
very not normal. Because it was push.
Yeah, but that was in the past. Jedi powers don't exist. It's not, the push has happened. It's of no concern anymore. All right, it's just the weight. Which way does the weight act?
Down.
So which way will the acceleration be?
No.
Yes. I have only one force acting on it, it's downward, so the acceleration has to be downwards. Which means there's no acceleration horizontally. Which means there's no velocity change horizontally. Only vertically. So if there's no change horizontally, that means however fast it's going horizontally at this point, that's how fast it's going horizontally the entire time. So at this point, it's got some downward velocity and it's got a horizontal velocity. So the actual velocity is going to be the sum of those two. Little Pythagorean theorem, find out the actual value. But what I care about is, I know it goes 1.2 meters horizontally. I know how long it takes. If I want to figure out how fast it was going, well, I just divide the distance it travels horizontally by the time. Officially, that's how you find average velocity. However, since it doesn't change horizontally, that's the value of the entire time. So therefore, the velocity horizontal, or which, go ahead and say it, it's the initial velocity, is equal to 1.2 meters divided by the 0.37796. I'll stop there. And you come out with how fast it had been going.
$3.1749. You want me to keep going?
Units?
Seconds.
I think you said it.
Yeah.
So I think that's an example similar to the master
Well, how do you find speed? Because it's asking speed, not initial velocity.
That it,
Meter seconds.
Yeah.
initially it was all horizontal, vertical is 0. So that would be the initial velocity would be that way. Initial speed, because there's no vertical component, is just that. Yeah. Questions before we extend it just a little bit farther?
If we did C squared plus D squared, would we come up with just a similar answer equals,
Come up with a similar answer?
or the exact answer?
No, well, if I was asking, what is the velocity when it is, now, what's the velocity at this point right here? Or what's the final speed? Let's do it simplified.
Well, if it's done, it's zero, right?
Well, okay, when physicists ask what's the speed when it hits,
Uh-huh.
they're talking about that moment just
If it's
before
like
contact. It's just the language physicists used and you're just supposed to know. So,
Would it just be gravity at that point?
well, at this point right here, the horizontal, it got two components, horizontal and vertical.
Mhm.
The horizontal piece is 3.1749 meters per second.
Mhm.
The vertical piece, well, I have something that I just dropped. How fast, what's that vertical?
That's the acceleration due to gravity.
That's fine.
Okay.
So 9.8 times 3.7796, which is about 36. We'll just pretend.
Yeah.
Um,
37.04008.
So right before it touches the ground, I have two components. I know that my horizontal component is 3.1749 meters per second. My vertical is 37.0, that seems awfully. Sorry, that's 0.3, so it's
Okay.
3.7, there we go. That makes more sense. Yeah, that 37
Yeah.
meters per second is about 70 miles an hour. And I feel pretty confident if I drop something from that height, it's not going over 70 miles per hour when it hits. So Pythagorean theorem to find the final speed, 3.1749, 3.704. The final speed is just whatever that is.
And it should equal that, right?
What, the 3.17?
Yeah,
No, that's the horizontal piece of it.
okay.